so it's been running for a few minutes now, maybe 4 minutes, and I can just show you what we're seeing already. And that's hard to see, but you can see like something is plating onto this skinny negative graphite electrode. You can see a little bump there. And again, let me just conclude right now that that's zinc elemental metal. So we have two instances now where elemental metal collects at this negative electrode. The big question is why? So can we theorize why elements, metallic elements in particular, are plating at this negative electrode? And the negative electrode is where electrons are streaming out from. So the battery, the negative terminal of the battery sort of shoots electrons out into the wire, which go into through the alligator clip into the graphite electrode. So electrons are streaming out at that point in time. If copper in solution is being attracted to this negative electrode, it might make logical sense to suggest that for some reason copper, when it's in solution, is positively charged. Same with zinc. If zinc atoms in solution are attracted to this negative electrode, it's not a far-fetched idea to suggest that somehow those zinc atoms in solution are not neutrally charged. They're positively charged, and that's why they're streaming to the negative electrode. So interesting. I mean, that's no small kind of logical feat of logic itself. But this leaves two questions. So why does copper sulfate make positively charged copper atoms or copper things in solution when it dissolves? And why does zinc become positive when it dissolves? And we can assume that maybe sodium and sodium chloride or in sodium bicarbonate, when it dissolves, also becomes positive. So even more broadly, the assumption here is, and then which leads to the question is, why do metals, when they dissolve in solution, become positively charged? And then this is where it gets super interesting in terms of making leaps into explaining how bonding works, chemical bonding works. So why does sodium bond with chlorine? Why does copper bond with this sulfate group? Why does silicon bond with oxygen and silicon dioxide, which is sand? Why does hydrogen bond with oxygen in water, H2O? So we've never really answered that question. So we know that copper in solution, or we've deduced that copper and zinc in solution are positive. Can we then say that maybe when copper bonds with sulfate, copper is this kind of positive thing and sulfate is this negative thing, and that's why they come together, is because opposites attract. When zinc bonds with sulfate group, can we say that zinc is kind of positive and sulfate is kind of negative, and that's why they attract, that's why they bond in the first place, that's why they react in the first place? So we're getting even deeper into sort of an electrical theory of chemical bonding. And chemical bonding, is it nothing but electricity and electrical interactions? Is it nothing more than something that's negatively charged, holding tightly to things that are positively charged? This would be a super specific and radical theory of chemical bonds, and I do think, and I shall say, that we are certainly onto something here. So let me break out my whiteboard, and let's see if we can even get a little deeper and write out chemical equations. So we had a lot of experience writing out chemical equations in course 1, the chemistry of atoms. So let's see if we can dive deep. And remember, chemical equations model the chemistry that's happening. So let's see if we can write out the chemical equation of, let's say, copper plating onto the graphite electrode. So if you'll recall, all chemical equations are written such that reactants react and form products. So this kind of makes it easy. All you have to do is list the reactants over here and list the products over here. And then if you can balance it and adhere to the conservation of mass, even better. So we know that the reactants are copper cations, and I now know in the 21st century that it's actually 2+, so they're positively charged to the tune of 2. They are dissolved in solution, so I use this AQ, aqueous. I now And we know that sulfate is negatively charged, so it's a sulfate anion, so it's written 2 minus, and that's also aqueous. And evidently we are forming copper metal, so that's a solid, and it's no charge. The sulfate, we have no evidence that it's doing anything, so that just doesn't do anything and remains a negatively charged anion, which is redundant to say. Anions are negatively charged. And so, interesting, we have copper cations, which are forming copper metal, and we just in sort of any algebraic equation, don't worry, I won't get into too much out of it right now. If you have the same thing on each side, you can subtract it out, cross it out. So we can kind of just go ahead and cross this out, kind of pretend this is a little mathematical equation. And I'm just going to rewrite this again. This still doesn't provide us with any new information. So the other kind of piece or actor in this play is electricity. And so I'm going to write, and we know electricity is, the electrons from the battery, which is producing electricity, which is a flow of electrons, is streaming electrons into the solution, into the graphite electrode, which is meeting these cations. So let's consider electrons as a reactant. I'm going to write that as E. So I'm just going to use a symbol small e for electrons. An electron clearly has a negative charge. Now, one other thing to kind of balance this out is, what if I put a 2 right here? Let me do it in a different color. So now I have a charge of 2, a charge of 2 minus. So 2 plus 2 minus is 0. Plus 2 minus 2 is 0. And if I have 0 charge here, I have 0 charge here. So I kind of snuck in another form of conservation here. So we have conservation of mass, but here I kind of snuck in this idea of conservation of charge. So electric charge in the universe cannot be created or destroyed. And so that's actually, kind of snuck that in. So this is exactly what's happening at the negative electrode. 2 electrons are streaming in from the battery. They meet with this cation. This whole idea of cations is new and beautiful in and of itself. And this is how electrolysis works. And this is how 20 or 30 elements were discovered in the first 2 decades of the 1800s. This new invention of the battery from Alessandro Volta creates these electrons. You dissolve minerals or ores in solution to create these metal cations. These metal cations meet these electrons, and bam, out comes elemental metal. And so you can imagine if you have a solution with calcium, it meets electrons, you can produce calcium metal. So calcium metal was discovered during this time. And so this is the big idea. This is where we are right now, as we see exactly how electrolysis works. It pumps electrons into solution, grabs these cations, neutralizes them, and forms and out pops elemental metal.